So I'm going to start recording. And for Wednesday's lecture, what I did is that I went ahead and recorded what I wanted to discuss. So when you have time, please go through the recording. It's already posted on Canvas. So if you haven't yet done so, please look at the class recording for lecture 4. This has a few very important concepts. So, for example, we were discussing the introduction to feedback and what are the different types of feedback you can have. So, just like we had discussed, amplifiers can be of 4 types. That your input could be voltage, output could be voltage, input could be current, output could be voltage, input could be voltage, output could be current, and both input and output could be current. So that was true for amplifiers. For feedback systems, it's the same. Your input or your feedback quantity could be a voltage or current, and your output quantity could be a voltage or current. So depending on that, you will have 4 different types of feedbacks, and that's what we discussed in this recorded video. So please go over the recorded video because it is one of the most important concepts in this particular course, and we'll come back to some of those concepts later on as well. So I'll just quickly go through what we had in the slides that I had shown in the recorded lecture. So basically, I'm showing here the feedback network where you have a feed forward path. So this gain of A, which could be an op amp or a traditional amplifier. So this is the feed forward path from left to right. So this is your feed forward path, and this is your feedback path. So from your output, you're feeding back some quantity back to the input. That's why it's called a feedback. So from your output, you're feeding back something. And during that feedback, you also have a gain factor of beta. Right? So that's what it means. And then if you solve, this is what is showing that your output and input could be both voltages and currents. And depending on that, you can have 4 different types of feedbacks. So this is what we show in these 2 slides. And then here we solve the equation for feedback doing your nodal analysis. So this is something, again, you have learned in 31111, how to solve circuits using KCL and KVL, right? And if you try to solve this using KCL and KVL, you'll eventually end up with this equation that your overall gain after feedback, so where you have your feed forward quantity is A, your feed forward gain is A, and your feedback gain is beta. In this case, your overall gain in the circuit, that would be A divided by 1 plus A beta. So your original gain, which was equal to A, now gets divided by this 1 plus A beta factor. So your gain reduces. But then again, I discussed in the video, why would you want such a system where your gain is reducing? And that is because, I'm going to reiterate this, but please look at the video as well, where I explain this in a more detailed way, that sometimes this gain A, so what you see in this op amp or this amplifier, this gain A is not a fixed gain. Your amplifier, if you buy an amplifier from the market, it will say that, okay, it can have a gain of 100 or 500 or 1000. It usually says it will have a gain of more than 100 if it is not stabilized using the feedback. What does that mean is that because of PVT variation, process, voltage, or temperature variation, if you apply a different supply voltage, the gain will be different. If you're testing it out in a different temperature, the gain will be different. So these are called P, V, and T variation: process, voltage, and temperature variation. Because of PVT variation, your gain A could be anything. It could be 100, it could be 200, it could be 500. But that means that if you're applying a 1 millivolt input signal, your output signal could be 100 millivolt, 200 millivolt, or 500 millivolt. You don't want that uncertainty. If you want to avoid that uncertainty, what you do is that you apply a feedback system, and that stabilizes the gain. How does it stabilizes the gain? And of course, again, go back to the video. It says that it's a negative feedback system, and only negative feedback systems can stabilize the gain. So what happens in a negative feedback system is that eventually you end up with this equation, A divided by 1 plus A beta. If it were a positive feedback system, this equation would have been A divided by 1 minus A beta. Again, that depends on whether you have a positive here and a negative here. That's why you're calling it a negative feedback system, that you're feeding back some part of the output and adding it with a you multiply it with -1 and then add it. Or in other words, you subtract it from the original signal. That's why it's called a negative feedback system. That you have a minus term over here. If both of them would have been plus, then we would have called it a positive feedback system. And a positive feedback system usually leads to instability. In oscillator circuits, you have a positive feedback system. So let's come back to this equation again. And what we were discussing was PVT variation. That because of PVT variation, process voltage and temperature, your gain A will not be a constant. It could be anything. So what are we doing here? We are connecting a feedback network, and we are calling the gain is equal to beta. Now this feedback network could be a resistive divider. So let's say you already have seen how resistive dividers look like, right? So this resistive divider, where your signal is coming from right to left in this case, because your signal is coming from right to left, if you have two resistors over here, R1 and R2, they will create this resistive division between R1 and R2. So you'll have a feedback factor of beta, which is less than 1. And this is something you have solved in your homework 1, that if you have this resistive division, your gain is less than 1, right? So your beta is something that is less than 1. On the other hand, your A is something which is large, but it's not consistent. It could be 100, it could be 200, it could be 500. On the other hand, beta could be, let's say, 1/10, right? It could be a small value, which is much, much less than 1. So if you now look at this equation, your numerator is a large quantity. Your denominator is 1 plus A beta. Now, if you divide your numerator and denominator both by A, so you'll have 1 in the numerator, and in the denominator, you'll have 1/A plus beta, right? So this is the same equation. I just divided the numerator and denominator by A. So this 1/A term in the denominator, this is something you can ignore. Why can you ignore this? Because your A is large. A is 100 or 500 or 1000. You don't care. All you care about is that it is a large quantity. So you can ignore this term. What it will mean is that your gain will now become 1/beta. And if your gain is 1/beta, you already know beta is less than 1. So 1/beta is more than 1. So you still get a gain. But the interesting thing is that this gain is not dependent on your process voltage or temperature. So this is PVT invariant. It is a ratio of resistances. The beta factor is given by a ratio of resistances, and the ratio of resistance is invariant of the voltage. So let's say you had a voltage of 10 millivolt over here. The voltage division ratio that we'll get, if you have a 10 millivolt versus 100 millivolt at the input, the voltage division ratio will still be same, right? The voltage division ratio does not depend on the input for a resistive divider. So you already see that the effect of V is not there anymore. Similarly, we are not discussing all these details, but if you go into the equations of temperature dependence or process dependence, you'll see that whenever you have a ratio of resistances, that dependence goes away. So eventually you'll have a PVT invariant gain, which is called a stable gain, because if your voltage changes or if your temperature changes, your gain does not change. Your gain is fixed at 1/beta. That's the reason why people go with these feedback networks or feedback circuits, where you can stabilize your gain. Even though your gain reduces, it becomes much more stable. It becomes much more consistent. Okay, so that's why that's one of the major reasons why you would want to use feedback. So please go over the recorded lecture, which has all these things in more detail, and it talks about what would be the gains in the system, what would be the value of A, what would be the value of beta, what would be the value of the gain with feedback for different kind of configurations. So please go through these details, which is already recorded in the video. All right. So next thing we started discussing in the recorded lecture is that now you have seen two different ways of calculating things. So for example, let's say you have this kind of a network where you have a amplifier and you're providing an input to the amplifier. This is VS, which is the input to the amplifier. From the output, you have a feedback network which connects it back to the input. Now, again, this is a circuit that we have solved in the recorded video using two methods. The first method is using your KCL and KVL, using nodal analysis. which again, I'll assume that most of you already know how to do. So that's method number one, that you apply KCL and KVL to solve this circuit. What is the drawback of KCL and KVL? As soon as your circuit becomes larger and larger, as soon as you start having 5, 10, 15 resistances and capacitances, doing a KCL and KVL based analysis becomes very, very hard. Right? The circuit becomes complex. You cannot do the KCL and KVL based analysis anymore. You can probably still do it, but it becomes harder. The second method that we had discussed was based on feedback. And we showed in the recorded lecture that you get to the same answer if you solve it using KCL and KVL versus if you solve it using the theory of feedback. So again, that's something we have shown in the recorded lecture. Please go through it once again. I'll just reiterate. Today we'll look at the third method. The advantage of, so maybe I'll just write those methods down. So the first one is based on KCL and KVL. And the problem there is that as soon as the circuit becomes much more complex, you cannot use the KCL and KVL based methods anymore. The second method that we had looked into in lecture 4, the recorded lecture, is based on feedback, the A-beta factor. So this is called A-beta based analysis or feedback based analysis. And we showed that the final answer is same if you use method 1 or method 2. The final answer will be same, but this A-beta based method, it will assume that the amplifier is ideal. And you can still assume that the amplifier is non-ideal and take care of the non-idealities, but then again, this method will also become very complex. The third method that we'll see today is called a loop gain based method. And this is much general. It takes the best of both worlds. It takes the best of KCL, KVL based method and the A-beta based method. So it can solve a complex equation and it does not have to assume that the amplifier is ideal. So we'll use this loop gain based method in today's lecture. All right. So now if you are given this kind of a circuit, let's say your input is connected at the positive terminal, and keep in mind that this is something where we have already started discussing op-amps a little bit, but we'll go into more details. So what is op-amp? Op-amp is an operational amplifier. So it's basically, for all practical purposes, you can assume that this is a black box or a black triangle or a blue triangle, whatever. And what you have here is a positive input terminal and a negative input terminal. And then you have an output. So that's all an op-amp is. Now, if you're assuming, and the job of this op-amp is to provide some amount of gain. So if your input voltage is V plus over here and V minus over here, the job of this op-amp is to produce an output that is A times V plus minus V minus. Or you can call it V positive and maybe V negative, so Vp and Vn. So in that case, this will be your Vp minus Vn multiplied with A. So that would be your output of the op-amp. So the job of the operational amplifier is to provide a gain, which is A times the difference of the two inputs. Now, and again, while I'm talking about gain, it is AC gain. Again, there were probably numerous questions on the GroupMe chat on the VTC, the voltage transfer characteristic, and there were some confusion about the biasing points and the gains and so on. So I'll reiterate this again. In this course, we'll only be talking about AC gains. Amplifiers or MOSFETs or BJTs, they cannot provide you a DC gain. To draw an analogy, think about a steam engine, or probably a part of the steam engine where you are putting in water and then you are producing steam. The rate at which you are producing steam versus the rate at which you are putting in water, that can be called as your gain. Okay, your output to input ratio. But that's the rate at which you are producing steam divided by the rate at which you are inputting some amount of water. So let's just assume that you have a hot tub and then your input is some amount of water and then you are producing some amount of steam. So the rate at which you are producing the steam divided by the rate at which you are placing some amount of water in the cup, that is your gain. But to do this, to make sure this happens, you have to heat this stuff up to 100 degrees centigrade, right? Or 212 degrees Fahrenheit. That's the boiling point of the water. If the water is not at your boiling point, it will not produce steam. Does not matter how much water you are putting in. So that is your biasing point. That is called your biasing point. That's the point. That's the concept of DC biasing. That you need to have. This system will work only if you have it at a certain operating point. And that operating point is basically the 100 degrees centigrade or 212 degrees Fahrenheit, which is the boiling point of the water. If you're not heating it up, maybe I'll draw a Bunsen burner over here, something like that. If you're not heating it up, this will not work. At room temperature, this does not happen. So you have to create certain conditions to make sure that your system works in a specific way. In case of amplifiers or in case of BJTs or MOSFETs, that certain condition is called biasing. So biasing is placing this entire system at 100 degrees centigrade or 212 degrees Fahrenheit, and the gain is basically the rate, the ratio of your input and output, or rather your output to input. That is the gain. So gain and biasing are two different topics, and we'll discuss more about this as we go into more details in this course. So I hope that with this analogy, it is a little bit clear that what we are doing with biasing and why biasing is required. But what exactly is biasing in terms of circuits, that's something we'll discuss later. Okay, so for this example circuits, we have shown the nodal analysis in the lecture 4 recorded video, and the nodal analysis found out that if you assume an ideal amplifier, which means that the amplifier has infinite input impedance, zero output impedance, and infinite gain. So those are the three conditions of an ideal op-amp. That it will have an infinite impedance at the input, it will have a zero impedance at the output, and it will have an infinite gain. If you assume those three conditions, we showed that using nodal analysis, you can reduce the overall gain to this equation, 1 plus R2 over R1. But R2 is the value of this resistance and R1 is the value of this resistance. And that is why this configuration is called a non-inverting amplifier configuration, where your gain is a positive quantity. This is 1 plus R2 over R1. So the gain is positive. How you are solving it using nodal equation? Maybe I can quickly solve it for you. How you do it is that you draw the linear equivalent model of the amplifier that you have done on the right hand side. Again, if you are assuming an infinite input impedance, this impedance will not be there. If you have a zero output impedance, there will be no output impedance on the right hand side, and you assume that this has an infinite gain. Okay. Now, with this circuit, you can do a KCL and KVL based analysis, and then you'll come up with this particular equation. And while doing so, it is usually assumed that for an amplifier that you have a property called a virtual ground. What does the property called a virtual ground mean is that if you ground, let's say this negative terminal, the AC fluctuation. So if you're grounding this here, the AC fluctuations or the small signal fluctuations on the other terminal will also be equal to 0. Why is that? Because the amplifier has an infinite input impedance. So the voltage, which means that there will be no current flow at the input, which also means the voltage at the two terminals at the input will be same. If there is no current flow, voltage is the same. Imagine a resistance through which there is no current flow. So the VA, the terminal VA, or which is basically VP in this case, and VN, which is the other terminal, the voltages will be equal. So if this terminal is VP, this terminal is VN, and there is no current flow from VP to VN, the voltages will be equal. Yes, question.
When you say that the AC fluctuations are equal to 0, does that mean the average value is 0?
Great question. it still means that there could be a DC. The average AC is 0. I didn't say the average DC is 0. The DC point could be, let's say, at 500 millivolts. But it could be a fixed DC point, and that's what biasing means. That to make sure that this transistor, this op-amp works, you'll probably have to place a fixed DC voltage at both the inputs. And while I said that this point is ground, it's important to remember that this point is an AC ground, which also means that if you put a biasing of 500 millivolt, a DC bias of 500 millivolt at this point, it would still mean that your AC is 0. Because for a fixed voltage, there is no sine wave on top of it. Right? If this is 500 millivolt, this is 500 millivolt. Right? There is no fluctuation in this 500 millivolt. And if there is no fluctuation, there is no AC. So this point could be at 500 millivolt, which means that like this point has no AC fluctuation. The other point will also have no AC fluctuation because your input impedance is infinite in an ideal scenario. So this is called a virtual ground property. It's not an actual ground. Why is it called a virtual ground? Because it's AC ground. It's not an actual ground. You do not connect the ground to this point in the circuit. But in terms of AC, it's still a ground. There is zero fluctuation. What is zero? Zero is ground. So having zero AC fluctuation means that you have a virtual ground. And that's why you'll hear this term a lot in circuit design, that some point is a virtual ground. That only means that there is zero AC fluctuation in that case. There could be a DC voltage, does not matter. The AC value or the AC fluctuations are zero at that point. That's all that means by saying that a point is at virtual ground. Okay. So if you solve this, assuming that there is a virtual ground over here, which means that there is no AC fluctuation at this point or this point. Or in this case, there is, I should say, there is no AC difference between this point and this point. Because you're already applying a AC. Your Vs is an AC voltage. In this case, you're applying the AC voltage to this positive terminal. So what would happen to the other terminal? What would happen to this point? This point will also have the same AC fluctuation, so that the difference between the two AC fluctuations are zero. That's what virtual ground means in this case. That the difference between the applied AC voltages at these 2 points or the observed AC voltages at these 2 points are zero. So if there is a Vs voltage at this point, there would be a Vs voltage at this point as well. And if you solve that equation that, okay, I have V0 over here and Vs over here, you'll know that the ratio of, so you can already now guess that if this point is Vs, and you are required to find out V0 over Vs, right? From the theory of voltage division, you can already write what is your Vs over Vf, Vs over V0. Vs over V0 will be R1 divided by R1 plus R2. If this point is Vs, due to virtual ground property, which says that both of these 2 points has to be at same AC potential. If that AC potential is zero, then both of them are virtual ground. If that AC potential is non-zero, both of them are at the same AC potential. And that's again because of this high input impedance. That if point Vp is at a particular voltage, point Vn will be at the same voltage. If one of them is zero, the other one is also zero. If one of them is 10 millivolt, the other one is also at 10 millivolt. That's it. So if you assume that to be correct, this point is Vs and this point is V0, you already know what is the voltage division ratio of Vs over V0. That is R1 divided by R1 plus R2, because this point is V0. I'll just draw it in a different way. So this point is V0. You have the R2 resistance after V0. Then you have this R1 resistance, which goes to the actual ground. And Vs is basically the midpoint of R1 and R2, that is Vs. So you can already solve this. This is R1 divided by R1 plus R2. So what would be V0 over Vs, which is output over input? That would be a inverse of R1 divided by R1 plus R2. That's what we are writing here. Right? And if you look into the previous video, you'll see that we come to the same equation using the A beta based approach, which was the second approach, the feedback based approach. Please go through the video if you haven't done so already. Now this gain, this is the gain of the circuit, the AC voltage gain of the circuit. This gain is called A infinity. Why is it called A infinity? Because here we have assumed the ideal op-amp condition. We assume that you have infinite input impedance that makes sure that you can have this virtual ground property. You assume the zero output impedance and you assume an infinite gain. Because of the infinite input impedance and the infinite gain, this is called A infinity. So this is the gain of the circuit, assuming the ideal op-amp conditions. But the overall gain of the circuit, if the op-amp is not ideal, if the op-amp is a non-ideal op-amp, so this is very easy to solve using the first method and second method. It is not very easy to solve if the op-amp becomes non-ideal using the two methods that we are mentioning here. That's why we learned this third loop gain based method today, and your homework 2 will be on the loop gain based method. Homework 2 has already been posted. The deadline is September 15th, so you have 2 weeks for that. But today we'll start learning what is this loop gain based method, which will be there in your homework number 2. So in the loop gain based method, it says that the overall gain is this AVS, which is A infinity divided by 1 plus 1 over tau or 1 over t. And which means that your A infinity is AVS when t is tending toward infinity. If t tends to infinity, this second term in the denominator goes away. So your A infinity becomes almost equal to AVS when t is going toward infinity. Now the question is, what is t? T is actually equal to your A beta. T is called a loop gain. Why is A beta your loop gain? Because remember that the feedback says that you have a feed forward network with a gain of A and a feedback network with a gain of beta. Right? So this was your feedback circuit, that your feed forward path had a gain of A and the feedback path had a gain of beta. The multiplication of the feedback gain and the feed forward gain is called the total loop gain. This does not mean that this is the gain of the overall system. So if your gain output is V0 and if your input is Vs, V0 over Vs is not equal to A beta. Remember that, and we have already solved this. What is V0 over Vs? V0 over Vs is equal to A divided by 1 plus A beta. So that is something that can also be solved from this system using the KCL and KVL. Do you want me to do it now? Because I'm not sure how many of you have gone through the lecture video that I had posted. So if you want, I can show why this equation comes in. Okay, let's do that. So let's assume that this point is Vx. Okay, so what is Vx? Vx is Vs minus beta times V0, right? You can write this. So this point, the output of this subtractor, Vx is the subtraction of its two inputs. What is the first input? The first input is Vs, the original input. What is the second input of the subtractor? Beta times V0, because you are taking some part of your output V0, multiplying it with beta, and then putting it back at the input side. So Vx is Vs minus beta times V0. You can also write your V0 to be equal to A times Vx. Okay. Now from these two equations, what you can say is that, or basically from here you can also say that my Vx is equal to V naught divided by A. Now I'll put this back into my original first equation, which will now read V naught divided by A, that is your Vx, that is your left hand side, will be equal to Vs minus beta times V naught. Now this means that you can take this beta times V naught on the left hand side and then take V naught common. So you'll have V naught times 1 upon A plus beta equal to Vs, right? So what would be your V naught over Vs? V naught over Vs would be 1 over 1 upon A plus beta. So this can be written as A divided by 1 plus A beta. Clear? So this is how you get to this equation for the negative feedback system. If it were a positive feedback system, if both of these were plus, so instead of a subtractor, if you had an adder, then some of these equations, so for example, you would have started with Vx equal to Vs plus beta times V naught. That's what will happen for a positive feedback system. And eventually your equation will become A divided by 1 minus A beta. But for a negative feedback system, it's A divided by 1 plus A beta. Just remember that. So this is your V naught over Vs. And out of this A beta term is called the loop gain term. What does it mean to say that this is the loop gain? It means that if you break the loop somewhere, let's say you are breaking the loop, let's say at this point. So what is the total gain coming from the input to the point where you have broken the loop is A times beta, right? That's why it's called the total gain in the loop. The feed forward gain multiplied with the feedback gain, that's the total gain. It's not the overall gain. So it's a matter of terminology. It's a matter of terminology in case of circuit design. The loop gain is basically A times beta. The overall gain is A divided by 1 plus A beta. So loop gain is not equal to your overall gain. Always remember, loop gain is equal to A beta, and this is sometimes represented as T or tau in different books. Okay, now since we agree that your overall gain is this A divided by 1 plus A beta, so I'll write it as A divided by 1 plus A beta. What happens if you divide the numerator and denominator with the loop gain? Your numerator will become 1 over beta. Your denominator will become 1 over loop gain. So let's call the loop gain equal to T plus 1. So you're dividing the numerator with A beta. You're dividing the denominator by A beta. This is what you end up with. Now remember that if you go back to this feedback discussion what we were having, what is your A beta? Your A beta is the overall gain when A is infinite, when A is very large. This 1 upon beta is the gain of the system when A is very large. What is a very large quantity? Infinity. So when your gain is infinity, this 1 over beta is basically the gain of the overall entire system. And that is what we had earlier called as A infinity. So 1 over beta is A infinity, and the denominator you have 1 plus 1 over T. So you see that this is the same equation, although represented in a different form. The equation is still the same. Equation is still A divided by 1 plus A beta, but this is represented as A infinity divided by 1 plus 1 over T. Because your A infinity is your 1 over beta when your A or the feed forward gain is infinite. And this is what we are writing as overall gain. Okay, this is the same equation. A infinity divided by 1 plus 1 over T. Now, this is what we'll show here is that this will be a more generic approach in solving op-amp based problems. And this is something we'll understand in the next page where we are solving a few problems. So what do you need to do when you have a non-ideal op-amp is that you just apply this formula. First, you find out the gain of the system, assuming that the op-amp is ideal. Find out the gain of the system, assuming the op-amp is ideal. That gives you A infinity. If you assume that the op-amp is ideal, you know what is A infinity. Next, you find out the loop gain and divide this A infinity by 1 plus 1 over T. That gives you the overall gain for the non-ideal op-amp. So the non-ideal op-amp's gain will be the ideal op-amp's gain divided by 1 plus 1 over T, where T is equal to A times beta. So you just need to find out what is T, and that gives you the solution for non-ideal op-amp. So in both of these cases, handling non-ideal op-amps was very hard. Using this approach, handling non-ideal op-amps will become much, much easier. Okay, so how do you find out the loop gain T in op-amp circuits? The motivation is clear by now, right? What we are trying to do and why we are trying to do it. So finding the loop gain T is basically, first you turn off all the independent current or voltage sources. So kill all the independent current or voltage sources. That means short all the independent voltage sources and open all the independent current sources. Like we did when we are finding the Thevenin equivalent resistance. It's the same method. Second, draw the linear equivalent circuit of the op-amp that we have already learned with the non-idealities. And then find out the overall loop gain, and we'll see from this circuit. This is the same circuit that we had drawn in the previous page and also in the last recorded video. So in this circuit, if you assume that the op-amp is not ideal, that is, if the input impedance is not infinite and the output impedance is not zero, you will end up with this particular circuit that is drawn on the right hand side. So this is your op-amp. So you have the gain of A times VD, A times the differential gain of the two inputs. That's the job of the op-amp, amplify the differential of the two inputs, the difference of the two inputs. That's the op-amp's job. At the input side, you have a input resistance, which is not infinite. At the output side, you have an output resistance RO, which is not zero. Okay, so that's why you have a non-ideal op-amp in this case. And solving this entire circuit using the first two methods becomes a big pain. So we'll use this third method. And the third method says that your loop gain T is equal to A, which is the gain of your op-amp. You already know what would be the gain of the op-amp. It's a non-ideal op-amp, so the gain will not be infinite. It will probably be 100, 500, 1,000, something like this. Multiplied with this feedback factor, this entire network, which creates your feedback term. Now, how to calculate that feedback term? Since we have already learned about the theory of voltage divisions, we know that what would be the ratio of two resistances or the division ratio of two resistances when they are placed in series. So we'll just use that formula in a cascaded manner. So you see that there are these resistances, but one resistance comes after another. So we can use the theory of voltage division in a cascaded manner to find out what is the overall loop gain. The overall loop gain is A times beta. What is beta? First of all, beta is the voltage division ratio. The first factor over here is basically the voltage division ratio between, let me remove this so that it is clearer. You have this resistance R0 at the input side, correct? You also have a resistance looking into this. Let's just assume that that resistance is Ry. Let's just assume this point is Y, and the resistance looking into the point Y is Ry. That's it. You don't need to calculate what Ry is at this point. Just assume that the voltage looking into or the resistance looking into this point is equal to Ry. Now you have two resistances. One is RO, the other one is RY. You know how to take a voltage division between the two. That is RY divided by RY plus R0. Next, you go further. You see that there are two parallel paths here. One parallel path goes through this R4 to ground. The other parallel path goes in this direction. If you have a voltage and if you have two parallel resistances, does the voltage get divided? No, right? You have two parallel resistances. The voltage does not get divided between the two. Voltage is same. Current can get divided between two parallel resistances, but voltages are same. So you'll not even have to consider this R4. You just go on in your merry way to this left-hand side through R2 and then through these resistances. Again, if you are going from right to left over here, what do you see? You see this R2 resistance, and then again at this point you see a complex resistance. Whenever you see something complex, just assume it to be a simple resistance of Rx or Ry or Rz, something like that. So now you see a complex resistance. Assume that the complex resistance is Rx. You have a voltage division between two series resistances. One is R2 and the other one is Rx. Write that down. Rx divided by Rx plus R2. So now you are at this point. Again, you see that there are two parallel paths. One parallel path goes through R1 to ground. The other parallel path goes through R input, R3, and then ground. What you are interested in is how much of this voltage is available at the input of your op amp. So what is the voltage that is available across this R in? What is the voltage that is available across this input resistance? That's the only thing you are interested in. And that's why you are doing all this. That what is my feedback factor? How much voltage I am getting back at the input of the op amp from the output. That's all you are interested in. So now you have two parallel paths again. One is R1, the other one has R1 and R3, Ri and R3. Which part you are interested in? You are interested in Ri and R3. And you already know because there are two parallel resistances, R1 and this combination of these two, the voltage will not get divided because it's a parallel resistance. So this point's voltage, again, you will not even consider this parallel resistance, just like you did not consider this parallel resistance at all. So from this point, you'll consider the path that goes through the R in and R3. And here, you're interested in knowing how much voltage is available across your input resistance. And that is again a simple voltage division, R in divided by R in plus R3. Yes, question. Why is it not negative Ri? Yes, that's a good question because of the directions that you are talking about, right? So the way we are considering the gain of the op amp is A times Vd, and at that time the way you consider the polarity of Vd is that this point is a plus and this point is minus. But when you are thinking about the voltage that is fed back at the input, you're going from right to left, right? So you're considering the current is flowing from right to left. The voltage developed will also be from bottom to top in this case, in terms of the feedback factor. In terms of the original voltage that is coming in, that part you don't care anymore. That part is inside this factor of A. So you're only considering what is being fed back. And in terms of the feedback, it is this. Okay. But yeah, that's a good question. That why we are not considering the polarity in this case. But even if you consider the polarity, you'll see that you end up with the same equation. So all right, is this clear? That how did we find out the loop gain? Yes, question. Exactly, very good question. Look at the first point. Turn off all the independent voltage or current sources. Remove all the independent voltage or current sources. You had this voltage source at the input. You are connecting it to ground, you are shorting it, because while doing this loop gain equation or while you're trying to find out the loop gain, you don't have to consider the effect of that input voltage anymore. The loop gain is independent of the input voltage. So why would you even consider it? Right? Next question.
The part that we find
Yeah.
That's the ratio of the voltage after R0, right? That's
Right.
That to RD, that's our like out of the
So which part you are referring to? So the volt,
oh, call that corner like
this point.
Yeah.
Yeah. So it's VA, or let's call it VY, because we are calling this point Y and the resistance RY. Okay.
So we're trying to find VY over V, right? That's like the
No, you are trying to find out the voltage at this point. So let's call it VO. So you're trying to find out VO over VD. Why? Because you want to consider the effect of this output resistance. If you just consider VY over VD, you forget about this R0 resistance, right? So which is not the correct thing to do. You're thinking about all the non-idealities in the op-amp. And RO, this output resistance, is one of the non-idealities in the op-amp. The only way to consider this is to start from this point. You do, right? RO and RY. So that's the first voltage division. Yes, more questions. Perfect. That's a great way to understand this and explain this. That why are we considering VO and not VY? Is because if you change your op-amp, your RO might change. Right? So how would you, so let's say you analyze a circuit and then you figure out that, okay, I could not find, so for example, the 3130 op-amp, which is hard to find, the 3130 EZ right now. So most of you are probably buying the 3130 MZ, right? So if that op-amp has a slightly different RO, all your analysis will change. And that's why you want to consider the effect of RO as well in the overall analysis when you are doing the loop gain. Okay. Any more questions? This is great, guys, because I wanted this part to be made more interactive, because this is a very, very important concept in all circuit analysis that we'll be doing in this course or in later classes as well. And if this part is clear, many of the things in this course will be very easy to do. More questions?
So to get RY and RX,
yeah,
you basically just, is it in any sort of parallel split, you just put like that RY was its value, RX was its value, and then solve from there. So it's simple.
So whenever there is a series split, you mean, like parallel split does not matter in case of voltage division. So if it's a voltage division, parallel resistances don't matter. Only series resistances matter. So you have to see what is in series. You have RO, then in series you have RY, this entire chunk of resistance. So you have a voltage division between the two. Next, you encounter this parallel R4 and a complex resistance. But because this is parallel, you don't consider it. You go on in this direction.
Right. But because RY, you already made it equivalent to R4 in parallel, right? Where
yes.
So that's not just factored in.
Of course, it's already factored in. So that's also a good question. That what is the value of Rx and R1? That is something you can write by looking at these resistances. So for example, Rx. What is Rx? Rx is the resistance looking here. And that value is R1 in parallel with Ri plus R3. R1 in parallel with Ri plus R3. That's your Rx. Similarly, what is your R1? Your R, maybe I should go back there because this part of the class may not be able to see it very well if I'm standing there. So Rx is R1 in parallel with Ri plus R3. And Ry is basically R4. So this R4 resistance, let me now put this back. This R4 resistance in parallel with R2 plus Rx. So this is the way you should analyze. So you have already simplified things enough, but then again, to find out the values of Rx and Ry, you have to use these equations. And that's it. That's all that is there in loop gain analysis. So this is only one problem that I have looked into in detail in class, because I wanted all of you to understand what is going on. The second example is just another way of looking at it, and just what it is doing is that it places the voltage input here instead of having a voltage input at this point. That does not change the analysis at all. It's the same setup analysis again. And the op-amp, you are representing it as a transconductance times input voltage instead of A times input voltage. You are doing it as transconductance times input voltage. So you have a current output, and then you have a parallel R0. And you are trying to find out what is the A beta factor in this case. So just go over it. It's the same set of formulas, same set of concepts. It should be very clear to you if you have understood the example one. Okay. We'll continue from here in the next lecture.
That's what I like. Kind of go over my head.
Sure.
So, this is like the very first start. With your offense, I mean, yeah. So because you said infinite input is defeated, so that's a virtual ground, right? So that means that you can just do that before this and make it that's
the ideal of and it's very well, as soon as you make it non-ideal, it becomes much more complex.
Okay.
Right. So what we are trying to do is how do you solve the non-ideal of it? Right. Ideal of them is very easy. So you can do it just by looking at it. Yeah.
Okay. All right. Awesome. Thank you.
So this case, this is for so this is like
Vortex transfer calculation.
this is for the invert, right?
Yeah. So this is for an inverting amplifier. And this is also for a digital inverter. So if you have taken in digital class, you'll be familiar with this. That is the VTC for a digital inverter.
I was confused the last time. Like this, like was like this way. There was another one.
Yeah.
And this could be 0, but it could be any number. It depends.
So, but that's bias. That's your boiling point of the word. If you don't put it at the boiling point, you won't get a reaching mark of the CP. So putting it at the boiling point is biasing.
And the Q point.
Yeah, that's the Q point or the biasing point or the boiling point.
It's not necessarily between like the half of the.
It's not necessarily, but usually it is. So if you have a plus 5 volt and a minus 5 volt, you'll see that you are asked to bias it at 0. Right? That means you don't have to bias it at all because 0 is not biasing it. If you have plus 5 and 0, then you'll probably bias it near 2 point. Because the VTC will anyway look like it. So if you are biasing it in the middle, you will probably getting a good amount of
Now I got it.
So, RX and RY is the combination of systems.
Yeah. So you're just implementing the complete network of ranges because the response RX or RY whatever.
Will RX and RY relatively stay the same equations, or will we actually derive that?
So that could be for each problem that could be different.
How, when you like place it down, how would you derive what the?
That is something we have already discussed. So for example, if you have 2 parallel resistances, so let's say your RX is 2 parallel resistances. You know that it is R1 in parallel with R2. If it is 3 parallel resistances, you know that it is R1 in parallel with R2 parallel with R3. And if it is 3 parallel resistances plus a 3 resistance, you know it is R1 in parallel with R2 in parallel with R3 plus R2.
But how do you know where to put RX, and how do you know that RX is R1 so low?
Oh, the RX is choice of RX is arbitrary. You do not have to. So why you are saying that this point is RX? That
Like why does RX and RY exist?
it does not exist. It's something that helps you to do that. What exists is just this RO, R4, R2, R1. These are the exist. These are physical resistors.
So you're saying RY here is R2.
RY is R4 in parallel with R2 plus RX.
Okay, I got you.
Yeah.
Wait, R2 plus RX.
R2 plus R2 and RX are in series.
Okay.
And R4 is in parallel to that.
And that means so RX is here. So RX could be
RX would be R1
parallel RI
plus
plus
R3.
R3.
Exactly.
Okay.
So this is
Okay.
so RX does not physically exist. RY does not physically exist. This is just helping you to do the calculation.
Okay.
Yeah.
All right. Yeah. Thanks. That something. And when will lab start?
6th of September. So next week 6.
Okay. All right. Thank you.
I didn't get it.